Okay, so hopefully you can see my screen
Yep.
now. Okay,
I'm hearing you.
and you can hear me. Good. Okay, so this talk was something that Ruth and I thought we should kind of put together as a sort of bit of a overview of what we're going to do for much of the rest of the workshop in terms of thinking about acoustic whale detection. So again, apologies to all the experts out there. I'm just sort of trying to touch on the various elements of this, and I'm kind of an amateur in it. But as I said, we thought it might be useful. Not everybody knows everything about while. So, okay. So here's our sort of general elements of the problem. We're actually interested in producing a southern resident killer whale detector, and to some extent have done so. Basically following this through, I'm not sure, you probably can't see my cursor, but if you can, we're starting from a, killer whale making a call. That call, produces sound that propagates through the water. To the next stage is the hydrophone. The hydrophone then samples the signal that it detects, produces some audio data. We do various sorts of analysis and processing on that data. We produce data products, typically spectrograms, and these spectrograms are becoming the input to various types of machine learning things. Machine learning is designed to detect whether or not the sound that was heard via the information in the spectrogram can be attributed to a southern resident killer whale or not. So what's our challenge? We want to build a reliable, robust, end-to-end, real-time whale detection system. And really, we want to integrate it into the forecast system that Ruth outlined at the top. The forecast system is essentially a data synthesis tool whereby it synthesizes various types of data sources, things like visual data, hydrophone detections, and it synthesizes those using a movement model, essentially. Okay, so I'm just going to go through various things. I'm going to focus a bit on sound first because we don't have any talks on sound specifically, but everything's implicit on sound propagating from the killer whale to the hydrophone for what we're doing. So killer whales produce sounds using phonic lips, and they're pretty good at directionally focusing that sound. Two major types of vocalizations. Calls, which are the things we're primarily interested in terms of detecting the whales. These occur at relatively low frequencies, say 1 to 20 kilohertz, and they have durations of typically seconds. And then they also make sounds that are echolocations, which thus far we haven't taken much advantage of. Those are at higher frequencies, and they're typically about detecting targets, i.e. prey, and spatially positioning as well. So, and they occur on very short millisecond durations. Okay. So sound propagation in the ocean. How does the sound get from the killer whale to the hydrophone? And does it indeed get there? Okay, so sound propagates as a compression wave. So that just means that the pressure fluctuations in the seawater are in the same direction as the travel of the wave. Sounds pretty much away from the immediate vicinity of the source, governed by a linear wave equation. That makes things fairly simple. It makes it relatively straightforward to model these things. It also implies that the analysis that you use can be based on spectrograms. The solution for the wave equation is just a traveling wave that's formulated in terms of signs. We have to think about the amplitude of the sound. We have to think about the frequency of the sound. We don't worry too much about the phase, and the wavelength of the sound is related to the frequency of the sound, essentially. The point being that we can basically model and analyze sound using sinusoids, essentially. So that'll lead us to why we use Fourier analysis and spectrograms for everything. The fact that everything's mostly linear means that we don't have to deal with a lot of complexities associated with wave-wave interactions. One consequence of the sound following the simple equation is that sound waves all travel at the same speed regardless of their frequency. That means that sound propagates as coherent entities. A lot of waves don't do that. Ocean waves don't do that. Long waves propagate faster than short waves in this case. So sound has some nice properties, which is obviously why, we and other animals have evolved to use it for information dissemination. What else? Sound speed, as everybody probably knows, varies in the ocean, varies with essentially the density of seawater. This means the temperature and salinity. Those can vary a lot in coastal regions that we're concerned with. It also varies with the pressure of the water. And the speed is typically 1,500 meters a second, but there's some variation within this. One thing that happens is when you have variations in density and pressure, you can get bending of the sound rays. And of course, the famous illustration of this is this SOFAR channel, this sound fixing and ranging channel, which allows long distance communications at about 1 kilometer depth due to the waveguide that's provided by the ocean. Coastal areas are a little bit different because the temperature and salinity are often varying primarily in the horizontal. There's strong fronts, there's river plumes from things like the Fraser. All of those alter sound pathways in the ocean. So, okay, sound spreads. So sounds loudest near the source, sounds quieter away from the source. One of the reasons that the acoustic energy dissipates is that when sound radiates from a point source like this, you can see its intensity, its energy per unit area decreases as you move away from the source. Even directional sound, like a killer whale would produce, also has this attenuation or drains because you can't focus the beam super tightly, basically. So that's the main reason why sound will decrease with distance, but there's also energy dissipation. Eventually, sound will get dissipated through the action of the viscosity of the water, any particularly bubbles being present in the water, they absorb directly. And I also discovered this when I was looking into this. There's a pH dependence to sound, which I didn't know of, which has to do with the molecular resonance and relaxation of certain molecules that participate in the pH system. So that was kind of interesting. Big thing is low frequencies dissipate a lot more slowly than high frequencies. Okay, what are the other two things? Boundary effects, reflection and scattering. So we all kind of know about this. In coastal areas, this is quite important because we're often in shallow waters. So you get things like, you know, this is the seafloor, you'll get a signal and then it'll bounce off the bottom if the bottom's sufficiently hard and things like that. Similarly, sound signals can bounce off the surface. If there's irregularity, if there's irregularities in the surface or the bottom, and you can get scattering, and that's based on the size of the irregularities versus the wavelength of the sound, essentially. So scattering actually sort of spreads all the acoustic energy and kind of disrupts the signal, essentially. A bunch of other processes are possible too. You can get transmission of sound through the seabed, particularly for low frequencies. The seabed often, depending on the bottom type, can absorb sound. And in coastal regions, this is important. There's a lot of discontinuities in the seawater medium, things like fronts, pictoclines, particulates that can either absorb and scatter sound, reflect sound, or do all sorts of other things. Okay, next element. So we've talked about how the sound gets from the killer whale to the hydrophone and some of the things that people have to think about. What do hydrophones do? They're basically capturing the sound signal at the location that they're deployed. They typically measure acoustic pressure in micropascals, and you can sort of see that the typical numbers for acoustic pressure are much, much smaller than the pressure of the that you see in the ocean, hence the ability to use these linear wave equations. What do hydrophones do? They do transduction. They convert the mechanical or acoustic energy in the seawater to electrical energy voltage, and they do that using piezoelectric materials. And piezoelectric materials are just materials that, you know, when they're vibrated, an electrical current is produced and vice versa. What else does hydrophones do in a big picture sense? They do analog to digital conversion. The sound wave is essentially a continuous signal that arrives at the hydrophone, and you have to subsample that signal in order to produce a data set. And typically those signals are subsampled at very relatively high frequencies. 44.1 kilohertz is standard for a lot of audio recording. A lot of underwater hydrophones will do it in the hundreds of kilohertz or greater even. So there's another more subtle thing I won't really talk about, but this, once you sample a continuous signal, all of the frequencies that are much higher than your sampling rate can bleed into your signature. So they have to also use anti-aliasing filters. If you don't know what that is, it's kind of an interesting thing to find out about. And finally, the hydrophone's going to also do often does a bit of pre-processing of the data for cleanup quality control, may store the data temporarily or more longer term, and it often has to transmit the data if we want to do real-time systems. And we have a hydrophone session later on that's going to describe some of this in detail. I'm not going to talk about my aliasing thing, but the point is frequencies you don't resolve in your sampling can come back to haunt you. Hydrophone system. So one of the things that we're going to talk about in another session is we have to get the signal from the hydrophone to the end users, essentially. So we want to get the recorded digital signal to the end users. We want to do this in near real time. So we're going to have a session later this afternoon on streaming hydrophones and the computer architectures that are necessary to do so. Okay, so now that we've gotten the sound, we've recorded the sound in the hydrophone, turned it into a digital signal or data file. We wanted to do a few things with it. This is probably the area that I know the best, I would say, of what I've been talking about so far. Here's an example of a time series of sound pressure level. That is basically a S1 call from JPod right here. You can see the durations of about 1.5 seconds. And this shows you the details of the call. This is like a 5 or 6 millisecond window that's just sweeping through this. If you look at my little movie here, you can see that the sound pressure signal is just made up of essentially sums of sinusoids like that. It's just periodic signals added together. And, you know, in a sense, you can model sound and analyze sound using this. This is the received sound pressure level. It's basically a sum of a bunch of different sinusoid at different amplitudes, frequencies, and phases. So it's relatively straightforward to analyze, and this is a pretty good description of the sound. So one thing is, if you look at these things, our brain isn't very good at picking out information by looking at time series or traces of audio clips. We can't really see much in the time series. But if you move into the frequency domain, for example, spectrograms, it's a much more natural way to look at these. So I'm going to move toward that. So if you acoustic signal processing, so one of the first things we do is we move into the frequency domain. We use power spectrum, and power spectrum are used to make spectrograms. And spectrograms are the inputs for our machine learning. So basically, since sound's made up of sine waves, Fourier analysis and power spectra are a natural way to look at things. So what does power spectrum do? It basically decomposes the sound amplitude by frequency, essentially. And it's a pretty complete way to summarize sound, basically, simply because of the fact that sound is made up of a superposition of sine waves. So here's again an audio clip right here again, this was the S1 call here. This is the time series. So this is the sound pressure level trace over basically 0.05 seconds. And this would be the power spectrum. So what does this show? This shows the dominant frequencies in that sound. You can see there's a peak at 1200 hertz, 2400 hertz, 3600 hertz, and so on. Basically separated by roughly 1200 hertz. The biggest one's here at about 5400 hertz. And that tells us the frequency makeup and the important frequencies in the call for this little clip right here. So there's a note. The one take-home message that I'm going to emphasize is that details matter. How you do this matters. So how you make a spectrogram matters. These time series have to be short enough when you're doing a window to remain stationary. So the sound can't be changing over the window you choose for the spectrogram, say. The audio time series must be long enough to resolve the dominant frequencies of interest. You've got to do some sort of smoothing, otherwise the spectral estimators are inconsistent. Yeah, you have to control the bandwidth. And you typically have to do other statistical things like tapering the sound to compensate for inadequacies in the Fourier transforms that you use to produce this. Spectrograms. So people, I suspect most people here have seen spectrograms and interpreted them. I've spent a lot of time sort of creating them and trying to create good ones, actually. So here's an example of how you create a spectrogram. So this is our, if you can hopefully see my cursor, tell me if you can't, by the way. This is the S1. Yes? Yeah. Okay, good. This is the S1 call. And basically what I'm doing is this little red dot line that's going through it is making little time segments. So the upper panel is showing the time segment associated with this red window that's passing through the data. And the bottom panel is showing the essentially the power spectrum of the time series clip in this time segment. So you can see where the dominant frequencies are of the killer whale call as the call evolves through time in this case. And you can see they change. They change in amplitude. They slowly drift in frequency, basically. And in this case, the harmonic structure of this. So what a spectrogram is just stacking together all these power spectrum from all these windows into a graphical representation like this, basically. I said it's a fairly complete representation of the sound. And the only thing it misses is it misses the phase information. So it loses the timing information. Is that a big deal? I just thought, okay, I took this spectrogram. So, and it said, here's the original call right here. I'm just going to play the S1 call. This was the original call like this. And this is the call that I derived simply from the spectrogram with the lost phase information. So I just randomized the phases or the timing, and I reconstructed the call from this, and I'll let you listen to that. You can see it's very recognizable as the sound, but it's got a buzziness and discordancy because it's lost the timing information. But, you know, most of the information is still there. And I think most of the buzziness has to do with the finite, piecing together the finite windows in the spectrogram. All right. Then I have another video. Not going to play that yet. So what is one of the main things that people do with acoustic signals after they make spectrograms or before they make spectrograms? They say, well, it's too noisy. It has features I don't like. So what they often do is apply digital filtering to these kind of things. So what does digital filtering do? It basically is a way to somewhat subjectively alter the frequency content of the signal, the killer of the sound signal, to emphasize the things you're interested in, whale calls, and perhaps remove at least some of the things you're not interested in, like the ship noise here, basically. So here, for example, is a raw signal I took from some hydrophone that Ruth gave me, actually. And you can see, if you look at this, this is a 1 second clip. It corresponds to this area of the spectrogram. And you can see there's this, you can actually see the oscillations right here. These oscillations are 60 hertz oscillations, and they're basically associated with a ship passing by. So that's basically the frequency of the crankshaft turning in the ship and the direct drive. So that's the propeller rotation frequency as well. 60 hertz sitting there. If you listen to this, you'll see it's very strongly dominated by that low frequency signal, but you can hear some of the whale calls that are superimposed upon that. So as an analyst, you might say, I want to get rid of that ship stuff as much as I possibly can. You can't get rid of it all because, you know, the ship noise actually bleeds into quite high frequency due to things like cavitation pops. But I just applied a frequency, a low pass filter at like 800 hertz, basically a brick wall filter in the frequency domain. And I wanted to kill off the ship sound. So you can see this area down here is all now blank. So these low frequencies used to be the ship sounds. I've killed them off. And this is this signal now, low pass filter. And you can see these two things have kind of appeared that you can't obviously see in this. These are actually 13 kilohertz, like whistles or something like that happen at high frequencies that you wouldn't have been able to even see in the series without getting rid of the ship signal. If you listen to this, you'll see that the ship signal is a bit de-emphasized, not gone, and the whale calls are emphasized. Okay, so low pass filtering is a common thing people do to clean up and process signals, and it's often done as onboard processing. My final slide is about machine learning. So, okay, we've passed through all the various elements here, and now we've made a spectrogram that we like, and we now want to feed that into we want to make a machine learning algorithm that allows us to ask this question. Basically, can we predict whether or not the input spectrogram contains features diagnostic of southern resident killer whale presence? So, and we're doing this using a convolutional neural network in this case. Well, I'm not doing it, but Fabio and Oliver and various people are doing that. So in my language, this would be a non-parametric nonlinear model. How do CNNs work? Essentially, you train CNNs based on annotated data. So you have spectrograms and you have in metadata on those spectrograms that say whether or not a killer whale was present or a southern resident killer whale was present during the time that spectrogram was taken. That's called in-sample validation if you're into statistics. You often then validate, after you build a model, you then validate the performance using an independent data set, out-of-sample validation, and you may do further testing on that. And just to link this up with what was I just did previously, these convolutional neural networks, well, what are they, basically? So I sort of did my half-an-hour crash course in this before I wrote this. So what do? They extract features in the spectrogram that are indicative of killer whale presence. They do this by convolving the image with a filtering kernel. So they're just doing filtering like I talked about in the last slide. The trick is that they are adaptively learning those filtering kernels, basically, by comparing, they're trying to pick out the features that are the best, most diagnostic of killer whale presence, get rid of the features that aren't, and link those together in certain ways, basically. So it's basically a sort of fancy application of filtering, digital filtering. So, and we're going to have a machine learning session where someone who actually knows something about this is going to talk about it. So my final slide is just the wrap up here. So what I did based on my direction from Ruth was just try to talk about the various elements of this problem. We start with the killer whale call. We want to see whether the hydrophone is able to classify and detect that through the various stages. So, and I'll wrap up there. Thank you.